if you have undersized pulleys on a conveyor system, head pulley, tail pulley, right, even the bends through the system, if the specification of the belt manufacturer for that particular belt, that particular application calls for an 18-inch diameter drive roller, but you go to the system and you do all the due diligence and get your information, you come back and find out it's got a 12-inch diameter drive roller, immediately what's that pop in your head possibility could happen to that conveyor belt in the field? Assuming everything else is correct, assuming the tensions are good, everything else is good, but now we have undersized pulleys. Are undersized pulleys that big an issue? Yeah, it's a huge issue, isn't it? Now, here's the next question. How many of you guys have been in the field working with customers and find out that their pulleys are all oversized? Everything you go to, you see is way bigger than it should be. Is that the case or not the case? Yeah, that's never the case, is it? That's really rare. Everybody's too small, aren't they? I mean, you go across the board anywhere.
Good salesman.
Yeah. Yeah, you go anywhere in the world, you're always going to find the pulleys are always too small. They're always going to be slightly under spec from manufacturer specifications. And granted, there's always a little fluff number in that manufacturer specification as well because they want to protect themselves. But in general, they're always going to be too small.
When we're talking about recommendations, industry standards versus real-world applications, pulley diameters that's probably one of the most obvious differences. And again, going back and picking on OEMs, they're pretty bad with, especially when you get into people who are making portable units. That they're more interested in figuring out how it can get down the road than how anything's going to perform.
Don't a lot of the pulley specifications based on 100% tension also?
Now, that's a good question. Mike,
Well,
you want to field that?
Daryl? See, yeah, professionally I did that.
If you look in most manufacturers' catalogs, and when you go to the part that says minimum pulley diameters, you'll notice there's a 0 to 40, 40 to 60, and or 40 to 80, I think, and 80 to 100%. So we've discussed earlier that most of your conveyor systems are running somewhere between 30 and 60% of the working tension of the belt. So you don't necessarily have to go to that 100% pulley diameter to feel like you're doing the right thing. But you need to know your systems, you need to talk about it. And Dick's going to address this a little later, but primarily minimum pulley diameters for conveyor belts, as far as the manufacturers are concerned, isn't what it used to be. Our adhesions are, when I say we, I'm talking about the industry. Our adhesions are fairly high now. We don't see a lot of problems with belt delaminating like we used to back when it was made out of cotton and leather. Basically, when you go look at that minimum pulley diameter, it's going to address the things that take place in your system. But Dick will talk about something a little later that is more relative to it than actually the belt construction. But basically, when you look at a catalog from your manufacturer, whoever supplies your belt, you'll notice that they'll tell you, 0 to, I think it's 0 to 40, 40 to 80, and then 80 to 100%. And you just select where you think that belt is. So that allows you to creep down in on a 330-pound belt from going around an 18-inch diameter pulley down to something in the neighborhood of 14 before you really get in trouble with it.
How many people has it been around portable conveyors where they're running 3 plies around 8, 10-inch pulleys? A lot of hands, right? Well, that chart that Daryl just referred to and the belting manufacturer's specifications, it doesn't cover that. And it's if it's a smart operator, they'll know that they're expecting that to fatigue the belt more rapidly as a result of flexing it over too small of a pulley.
But I want you to kind of visualize something. This is always a good visual, I think. We got a small piece of 3-ply conveyor belt we're going to pass around, 3-ply 330, kind of standard stuff, bread and butter business, right? And this sample of this conveyor belt, just for your own visual point, just grab this sample and flex it like this. Just bend it and flex it, and then look at the side view of the fabric plies. And we'll pass this around. You guys can do this and look at it. And just think about what's happening as this conveyor belt goes around the system, around this roller, and the diameter's too small, the belt's got a fairly heavy gauge to it, right, pretty thick. And as it does this then, the length, in other words, the distance from the axle to the outer layer to the inner layer is different. So we know that the speed and the tension is slightly greater in this outer layer fabric. The speed is slightly slower. I mean, it's minute, but it's still a difference in the inner layer. And the center layer is typically known as a neutral axis. It's not elongating, nor is it compressing. In conveyor belt design, what do you think is most dangerous, compression or tension? If you had to speculate, what eats up conveyor belts faster? Raise your hand. Raise your hand if you say tension. Good. Okay. What about compression? Raise your hand if you think it's compression. Well, wait a second, my friend. I have a 40-year veteran in the back that's disagreeing. He says compression. Tell us why.
Because the belt will stretch. Your belt is designed with elongation in it. We either use the fabrics that'll give you elongation, or we give you a little bit of crimp in the carcass that allows for elongation. What we can't compensate for is compression. Fabric does not like to compress. So as you go around those pulleys, the compression is the thing that will kill your belt. We call it compression flex failure. And you see a lot of it in elevator legs. I don't know how many of you deal with elevators where you have a lot of tension on the drive pulley, but in the boot pulley, no tension. The splices come around. Typically, they'll build a splice that's a long splice. As it goes around that tail pulley, you don't have enough tension in the system to cause the outer plies to stretch, so the lower plies or the inner plies or the inner belt actually in the type of splices they use compresses and gets knuckles in it, and then as it goes around the pulley, it folds them over and the belt will fail right along the bucket line.
How many people can think of another situation where you can readily see compression in a belt? Anybody want to take a stab at that one? Joe said transition. We're going to talk about that in greater detail later on, and something you'll want to look for when we do our site visit. But compression will represent itself symptomatically in a transition violation situation.
You'll be surprised how many conveyors have bad transitions and how that's going to affect the splice. Sometimes it's visible, sometimes it's not visible. But the belt itself will delaminate, the splice very quickly gets eroded away and broken down.
And typically, when you see splice fatigue, that's still going on internally in the rest of the belt, too.
Yeah.
It's just that it's not visualized because you've got covers that are covering fatigue factors that are occurring inside the belt.
You know, if you have splice fatigue and separation, right away you're going to have ply separation if it runs long enough, or you replace the splice and do it again. That same force is being applied to the entire conveyor belt. So now we're going to have this flex fatigue, right? This whole process is going to be eating the conveyor belt up internally. There is a mechanism in the fabric that allows for tension. So here is a side view of a piece of standard woven conveyor belt fabric. We can pass this around, you get to look at it. 110-pound fabric, standard stuff, nothing special about it. Although it is made by Fender, but I'm sure it's special, stuff. But it's pretty basic, right? So it's going to see forces this direction, right? Tension, it's the warp. This is the weft across the width of the conveyor belt. Now, across the width of the conveyor belt, in other words, across the width of the conveyor belt, we have these filler members. Those filler members have a really specific purpose. Along the length of the conveyor belt, we have another type of filler member or another type of tension member. And that particular member has a really specific purpose as well. So take a look at this. We pass it around. And envision that at rest, the conveyor belt fabric looks like this, side view. As we start to apply load and force to this piece of conveyor belt, it takes off with product. It goes up the slope. It's increasing the tensions. The load's increasing. It's stretching, right? It's elongating through tension. It gets up to the head pulley. As it starts to really elongate, then we start to, and this is, I'm going to draw it kind of extreme so you can see it. Those filler members start to flatten out. So what we have now is tension and normal tension. So at rest or at normal tension, the filler members act as like little springs, kind of like little shock absorbers. And their design component in the fabric is to say, I need to be very compressible. and I need to be very compressible very fast, right? So as I apply load and force to this piece of conveyor belt fabric, as I apply the load and force, I have some mechanism in the fabric that allows that to concur, right? That allows that to happen. So I apply load, force, stretch, put tension in the conveyor belt. Those filler members compress, allows it to stretch. If I didn't have really compressible fibers, say it was steel, say just crazy stuff, those was little wires inside the belt, steel, and I apply load and force, now I have to make my tension members do the elongating, right? So I have to change the way they're woven, the type of fibers using the tension members to be them very elastic, right? Here's an example. Think of this. What's nylon famous for? When you think about nylon, what's the one thing you hear about nylon? Stretches, right? So we know that pretty commonly most conveyor weaves and design in the fabric, nylon is a favorite component. Nylon 6.6, pretty favorite component because it's got a really quick ability to compress and return to shape, compress, return to shape, right? So it's easily compressible in general. A lot of conveyor system materials or conveyor fabric components, yarns, have another type of fiber that's not quite as elastic, because if I have my tension member also made out of nylon, which has benefits but can be a downside too, if it's made out of nylon as well, it might stretch too much, right? So it's possible to have a conveyor belt that's an all nylon construction. It has benefits that we're going to talk about a little bit later on, but it has some downside to the fact that it might have to stretch a lot to get all that working stretch out of it, right? Because it's very elastic. So pretty commonly what you'll see is polyester used in the tension members because it is elastic, but not dramatically elastic. It's not quite as stretchy, right, as the nylon. So it allows us to have some give and some work into it, but not to stretch itself out of shape. So polyester nylon construction conveyor belt, pretty common stuff, right? For you guys, does anybody here deal with imported conveyor belting, bringing belt in from another country? Sometimes, yeah. And when you do that, do you notice the rating? The rating on the conveyor belt fabric is EP. What do you think it's EP? What do you think that would stand for if you had to guess?
Okay, hold on. Here's an EP answer right here.
Oh, it's a polyester nylon.
Okay, so why is it not PN? Because in North America we would typically say PN, right? Polyester nylon. Well, okay. What they're using is the chemical name for nylon, and they're using the chemical name for polyester, getting that EP short for, I'm not even going to try to pronounce it. But
something.
But and it's in your book, we're going to get to that after the break, but that's pretty common design. So we know that in the fabric, we see tension, we have this ability to compress at a really rapid rate, and we go back, we can relax. Now, let's do just what we talked about. Here's our system. Hope you can see this. This time we have compression. So instead of having forces applying load to that piece of conveyor belt fabric, stretching, elongating, compressing the filler members, no, in this particular case, we're compressing it together. The belt's being elongated as it operates through the system, stretch, stretch, stretch. It goes on the head pulley, and around the head pulley, it's coming back on the return side. It's doing what? Because on the load carrying side, if I'm the head pulley driving this conveyor belt on the motor, I'm really doing what to the fibers of that conveyor belt? Pulling them up the slope, right? Now that I pull them up the slope, I'm elongating this rope, this weave of the fabric. On the return side of the conveyor belt, I'm still the drive motor. On the return side now, what am I doing to those fibers? Pushing them away. So I'm stretching on load, and the more load it sees, the more stretch. On the return side, I'm compressing. So we know we're going to compress it at some rate. We know that we have really small pulley diameters going to really compress it, really push it together. Think about how there's no mechanism in the fabric. There's nothing built into the fabric that says compression can occur. Just study it a second, think about it. I have filler members that allow tension, but when I push it together, push the fabric together this way, there's no mechanism that says I can do that without breaking the belt down. And what's going to happen is that we're going to end up all these voids because as we manufacture the conveyor belt, the rubber goes through a state, starts to flow and starts to fill up all the voids in the conveyor belt. After class, after lunch, We're going to talk about a little bit of rubber chemistry and how that works. What you need to know is that you're going to end up with all these voids around the filler members, around the tension members, because the rubber's being pushed together, it can't elongate, it can't stretch, it breaks. Now I have millions of really small pin-sized voids in my conveyor belt fabric, and I happen to have an environment that might have water in it. What's the one thing that's common in the whole world? Water. All right, so now we got the biggest, strongest guy, and we're going to break right now. Biggest, strongest guy in the room, he gets his bottle of water, he puts the lid on it, and I say, reduce this down to a real small size so I can put it in my pocket. Is anybody here strong enough to do that? Can you compress water? Not really, not practical purposes here, right? So water is really incompressible. So I fill up those voids with water, and it's really incompressible. As it operates through the system under tension, what happens to those water molecules? If I can't compress them, and I know that I'm going to see load and elongation, I'm going to compress it. I got this filled with water molecules over time. Just like, yeah, it starts to separate that whole conveyor belt, doesn't it? It's hydrolysis. Hydrolysis effect says that, listen, I can't compress the water's got to go somewhere, and over a period of time, I start to move that water through the conveyor belt lengthwise, and as it moves through the conveyor belt lengthwise, it's uncompressible, starts to separate the fabric in the conveyor belt, and ply separation occurs. And it always starts in the splice first. We'll explain why this afternoon.